In this lesson, we'll show how to solve friction problems that involve a combination of different types of motion. We'll begin with a problem like this. We have two blocks that are resting on a board. When you pull on the top block, how much force is necessary to cause it to move? So here's the same type of problem. We want to find the force P needed to cause impending motion of this system. And first we'll consider the top block slipping on the bottom block. In other words, doing this. To figure out what force P is necessary to do that, we'll draw a free body diagram of this block. We have the weight, and that of course is 100 newtons. The normal force, N sub B, and the opposing friction force, F of B. Let's apply our equation of equilibrium in the y direction. We have N sub B minus 100 equaling 0. Solving, of course, N sub B comes out to be 100 newtons. Now we realize that we need this to be the limiting static friction force because we want to find P necessary to cause impending motion of it. Applying the friction equation, we can find F of B. And that's equal to mu, which is 0.5, times our value for N sub B, which we calculated to be 100. We get an answer then of 50 newtons. Next, with some forces in the x direction. Doing that, we have P, and we have minus 50. And this equals 0, of course. Solve for P, you get the answer of 50 newtons. 50 newtons will cause this block to slip on this one. All right, now let's look at the other case, assuming both blocks stay together and the system slips on the floor. In other words, it moves like this. To analyze it, we consider the system of both blocks, draw a three-body diagram, so we have 250 newtons here. The normal force up, N sub A, and of course the friction force, which opposes the motion. Summing forces in the y direction, N sub A minus the 250 equals 0. Or in other words, N sub A is equal to 250 newtons. Now let's find our maximum static friction force, and that's found from our equation of friction. We have F of A equaling our coefficient of friction, which is 0.3, times our normal value, which has been calculated to be 250. When you work this through, you get 75 newtons. Finally, let's find P. We have P minus 75 equaling 0. And so the value for P is 75 newtons. That compares with 50 from the previous situation, where block B slipped on A. Well, the answer is 50 newtons, because as P gets larger and larger, it reaches 50 newtons, causing this slipping, before it can reach 75 newtons to cause both blocks to slip. Now we'll look at a problem of this sort. The guy on the left is pushing on this refrigerator and causing it to slip on the ground. However, this guy is pushing on this cabinet, and it causes it to tip right in the corner. We'll consider a problem like this. And so here's the case where we want to find the force P needed to cause an impending motion of this 100 Newton block. Well, the possibility of slipping occurs. In other words, this happens. Or the possibility of tipping. In other words, this can occur. Notice that in this case, the normal force is acting at the corner, whereas in the case of slipping, the normal force is somewhere underneath the block. So we'll look at both cases and find the smallest P, because that'll cause the motion either slipping or tipping first. All right, so here's our problem. And now we'll analyze it by first assuming that the block slips rather than tips. So we draw a free body diagram showing the normal force over some distance x away, with the hope that x is never greater than 1 meter, the distance from here to here. We have our normal force up. We'll call it N sub A. Our friction force F of A. Our weight, of course, of 100 newtons. And finally, our force P. Now we'll apply our three equations of equilibrium. Summing in the x direction, P minus F of A must equal 0. Now let's sum in the y direction. N sub A minus 100 is equal to 0. We can actually solve this equation. We might as well do that. N sub A comes out to be 100 newtons. Now we can take moments. We'll do that around point A. We have 100x. And we have minus P times 4. And this all equals 0. Well, obviously we don't have enough equations to solve yet. We need one more equation. We'll use the friction equation. F of A must equal the coefficient of friction, 0.3, times the normal force, which of course we calculated to be 100. When you work this through, you get an answer of 30 newtons. We can put it up here, and we calculate a value of P being 30 newtons. That would cause, of course, the block to slip. We don't know if it's going to tip yet. We better check that. If P is equal to 30 newtons, and I put it in here, 30 times 4 gives us 120. And if I divide by 100, to get a value for x. It turns out to be 1.20 meters. Now we're in trouble. Obviously, x can't be greater than 1 meter. Therefore, the normal force has to be shifted over to the corner to cause the block to tip. In other words, the free body diagram now looks like this. N sub A is here. Here's our friction force. It's certainly not equal to mu n anymore, and I'll show that in a minute. And of course, here's our weight and our applied load P. Now, x is given. X is 1 meter. So with that known, x being equal to 1 meter, we can come back and deal with these three equations of equilibrium. This equation no longer applies. And that's because, as we stated, the block isn't going to slip. But we have the three key equilibrium equations. When x is equal to 1 meter, P will equal 25 newtons. That's the answer. As the force P is increased, the block will begin to tip and not slip. Notice, for example, what F of A would be. It would be equal to 25 newtons also, wouldn't it, from this equation? And since we know that the maximum friction force you can have for the problem is 30 newtons, we know indeed the block does not slip. Rather, as I said, the normal force is over at the corner and causes the block to tip over. Now finally, we'll do this problem. Here we want to determine the force P needed to cause impending motion of this 100 Newton cylinder. It's resting on a beam up here, and you can see that the force on the beam is 200 newtons. The coefficient of friction up at the top B is different than it is at A. So when you pull on the cylinder with a force P, we don't know if it's going to slip up here and roll down here, or possibly roll up here and slip down here. Let me show you how the motion would really occur. Rolling at A, down here, and slipping at B, it looks like this. Or of course, we would use F equals mu n up here. But then we have the other idea. Rolling at B, and possibly slipping at A, it looks like this. Where now we use F equals mu n down here because of the slipping effect. No slipping here, of course. Now there is a possibility that the cylinder could slip at both places at the same time, but that would be a very lucky incident. It'll either slip and roll at one point and not the other. And so here's our problem, and now we're going to analyze it and see exactly what happens. To do it, we have to draw the free body diagram of each member. And on the beam, we have the 200 Newton load. And we have the unknown reactions at C, Cx and Cy. We have the normal force over at B, and we have the friction force at B. I'll refer to this one as F of B. Now, we don't want to involve Cx and Cy in our solution, and so rather than find them through the equations of equilibrium, I'll simply use the mode equation around this point in order to determine the normal force over here. I think you'll agree, because this load is in the middle, the answer here would be 100. But basically, it's 200 times 1.5 equaling this normal force times 3. And so we get a result of 100 newtons. Now let's use that idea and work with the cylinder. Action-reaction. And now we have, of course, the friction force, which goes this way. The weight downward, which is 100 newtons. The force P going up. The normal force N sub A. And the friction force F of A. Do you see why the friction forces go as they do? P is tending to rotate the cylinder around its center in a counterclockwise direction, and the friction forces are rotating the cylinder in a clockwise direction to counteract it. Now we have a free body diagram of the cylinder, and now we'll deal with it. First, I'll write the three equations of equilibrium for the cylinder. In the x direction, F of B minus F of A must equal 0. Or to put it another way, F of B is equal to F of A. Next, we'll sum forces in the y direction. N sub A minus 200, and of course plus P. And that'll equal 0. Then we'll take moments around the center of the cylinder. P times 0.5 minus F of A times 0.5, and of course minus F of B times 0.5. And all this equals 0, of course. Now that we've written the three equations of equilibrium, the next thing we need to do is we have to deal with the friction issue. Notice that in our three equations we have four unknowns, and we do need a fourth equation. It's either going to have to come from mu n up in here or mu n down here. We'll assume slipping at B first and rolling at A. If we do that, then we have the equation of friction, which looks like this. F of B is equal to our coefficient of friction at B, which is 0.5. And then we have our normal force, which we know to be equal to 100. In other words, F of B will equal 50 newtons. Well, if you know this is the case, then F of B is equal to F of A. Consequently, down here, this will be 50, and this will be 50. Here, of course, you can see the 0.5s cancel out, And 50 plus 50 gives us P of 100 newtons. So in order to cause the cylinder to roll at A and slip at B, we'll take a force P of 100 newtons. But we need to check that. And so in order to do that, we're going to have to assume the other case can occur. That is, it can roll at B and actually slip at A. This may not be valid. So let's do it again. Applying the friction equation. Now, F of A is equal to our coefficient of friction 0.3 times n sub A. There we go. Of course, F of A now is equal to F of B, so therefore we can set this equal to F of B. That comes from up here, of course. Now to complete the solution, we notice because of this relationship, we can write F of A as 0.3 Na, and of course we can do the same thing here. So in other words, P can be written as 0.6 Na. Realizing that, I can come up here and solve for P. In other words, I can rewrite this equation as P over 0.6 minus 200, and of course plus P equals 0. If I solve for P in this equation, I get an answer of 75 newtons. Consequently, the cylinder will tend to roll at B and slip at A. And it ends the lesson.